Good evening. Good evening. My name is Samantha Hayden and I am a applied mathematics major at UNM. Today I would like to go over the process of graphing a function using derivatives. This will be most useful to students in Calculus 1 or students just trying to review. You should have a basic understanding of some algebra, and it would be helpful to have a graphing calculator just to check your results in the end. To start off, we're going to go ahead and identify our equation. This is going to help us because identifying our equation and what parent function that equation comes from will allow us to determine what other information we need to gather to display the correct behavior in our graphs. This evening we will be reviewing a polynomial function. Because we're dealing with a polynomial, there are certain aspects that are a little bit more important, like the zeros, for example. I have here a table with the multiplicities and how they react, just for a little bit of a refresher if you need one. So, finding the basic parts of your graph. This is before we get into the derivatives. To start off, because I'm dealing with a polynomial, that means that my domain is all real numbers, meaning I don't have any exceptions for my x values. But it's also important that I find my x and y intercepts, which is usually important for most graphs. Symmetry, which is always good to check, always helpful. And for polynomials, the zeros and multiplicities are incredibly important because they can cross the x-axis so many times. So here I have calculated the y-intercept and x-intercept. This should be a review, but if you need a little bit of time to look it over, go ahead and pause. Yeah. And here is where I test for symmetry, where you can see that it is symmetric about the y-axis because I get the same function. And then over here, I tested the multiplicities. Because I only have one of each x value, that means it'll cross the x-axis like a linear function. So now we're going to go ahead and find our derivative. So this is the first derivative. It should already be a review, but if not, here's a graph to the side of some properties. Remember, though, that the derivative is the slope of the tangent line on a curve from your original function. So this means that when we're looking for the first derivative and we're using the first derivative test, we're looking for when our slope is 0, because that means our tangent line is 0, which only happens at when the line is completely horizontal, which would be at a peak or a valley. So here I've calculated the first derivative. If you need some time to review, go ahead and pause to look this over. Here's a bit of an explanation about why we use the first derivative test and why it's important and why it works. So, and here's a diagram as well. So if you need some time to look this over, I thought it was helpful when I was learning it, so it might be helpful to one of you as well. Here I am calculating my critical numbers from my first derivative. This is crucial to graphing because my critical numbers will tell me if there's at my critical numbers, there's a possibility to have a maximum or a minimum. So I have to find my critical values and then test values on either side of those values to see if I have a max or a minimum. So here I've placed my numbers on a number line and have test values. I always suggest creating a table with all your information because it's a nice way to organize your thoughts. So here we have a function that is decreasing to increasing, meaning that it is going down to up. So it would be a minimum. Over here, we have increasing to decreasing, which would be a maximum. And then lastly, we have a decreasing to increasing once again, so that would be a minimum. So as you can see, the derivatives being negative or positive means that the slope of my function is either decreasing or increasing, and this is why the first derivative test works. So now that I have found out where the max and mins are, I like to plug in my values right away into the original equation so I can get my coordinate points for where those max and mins will be and how tall or low they will be. They will fall on the graph. Alright, so finding our second derivative. So this should also be a bit of a review. Just a second derivative is the derivative of your first derivative, and the second derivative will test concavity. So it tests concavity because it is testing the rate at which the first derivative changes. Okay, and it's important to note that you usually use a second derivative to find inflection points, but these are only possible inflection points. You don't always have an inflection point, only if the concavity changes from concave up to concave down or vice versa. Okay. So here I've calculated the second derivative, and I've also solved for 0. So these values right here will be my possible inflection points, but I will have to test the values to figure out if they are inflection points, and if so, where on the graph it's concave up and where on the graph it would be concave down. So here again I have put another table, which I think is always useful, and it always helps to organize all this information that you are getting from one equation. So here I have that when I tested the values and I plugged them into the derivative, the sign of the derivative is positive, negative, positive, and then that affects the graph of my function to be concave up, concave down, and concave up. Because I have because my concavity changes from one to another, that means I have inflection points. Now that I know that I have inflection points, I like to plug it back into my original equation to see what the y value of these inflection points will be. Okay, I know that was a lot of information really fast, but let's go ahead and do a recap to gather all the information that we have just found out about our function. So we're looking at a polynomial function with all real numbers for a domain. It crosses the y-axis at 0, 8, and crosses the x-axis at 4 points, 1, 2, 3, 4. Notice that there are 4 points because of the square roots. When you take a square root of a number, you have to have a positive and a negative. So that's important because it'll really mess up your graph if you don't have all of those. Also, we found out that it's symmetric about the y-axis, so that means it should look the same on both sides. And then we found out when it's increasing, when it's decreasing on our first derivative, which then allowed us to find maximums and minimums. Then our second derivative told us when it was concave up, concave down, and when those change, when it changes from concave up to concave down, which would be our inflection point. And so now all of this information, we have to put it all together. And that would be the graph. So for our graph, I have over here just the important coordinate points. Notice I didn't put the intervals because it can kind of get a little bit confusing having a bunch of numbers in parentheses. So I just put the coordinate points for us to use today. And then over here I have just some values to help me graph and a key. So I have labeled all these points where these key points that we have found throughout our presentation. So we know that the graph from negative infinity to negative 2 is decreasing. And then it's a minimum, then it's increasing. This here is the inflection point. So that means it's going to turn from concave up to concave down, go through these points, up and down. And that is our graph. So thank you very much for watching, and if you need any more information, there's a link in the description. Thank you.